Morning, everybody. Jim O'Donnell, there's my contact information in the lower left-hand corner. Thank you once again for attending. We are recording this. We can issue PDH credits. Just send myself or Gina O'Donnell an email about that. And then finally, thank you for helping me out with Buck, Tim Green, Rickiditis, as well as Gina O'Donnell. So let's get started. Today we're going to talk about dedicated outside air systems. DOAS is the acronym. We're going to go over the psychrometrics, and then today is going to be part number 1. Oops, my screen. Okay, so for today's focus in part number 1, I'm going to be focusing on space temperatures that are in the range of 75 dry bulb 50% RH down to about 65 dry bulb 40% RH. So our leaving air dew point temperature is about 55 degrees, down to about 42 or so. You can achieve these dew point temperatures using refrigeration systems. For part 2, that's in September, we're going to be talking about lower space temps, lower dew point temperatures, approximately 40 degrees and lower. And then with that type of equipment, you're going to have to use passive or active desiccant wheels. And then just on our site chart, just roughly where we're going to talk about today is part 1 and part 2. And then today, I'm going to focus on DOAS units, but I'm only going to focus on the cooling and dehumidification operation of the DOAS unit. And then especially try to focus or make it apparent to you to worry about or just be concerned about the dehumidification that you're providing with your DOAS unit. 5 things going to go over today. First part is a partial review of psychrometrics. Psychrometrics is a study of thermodynamic properties of moist air. That water vapor in the air, causes not issues or problems, but what we're highly concerned about. We're going to design or operate at all cooling and heating loads and ambient conditions, whether it's hot out as well as moist or dry, and then also whether it's cold out and whether it's moist or dry at the same time. You've got to satisfy your space conditions. What that means is you really should comply with ASHRAE 55 for thermal comfort to try to stay in that little light blue and pink box from a comfort standpoint of the occupants. And then the other thing, once again, that we're trying to emphasize today is that you should be concerned with humidity control, with your moisture removal. This chart, well known, a lot of people have probably seen it before, but you want to try to maintain your space relative humidity in that nice green section, where from 40 to 60%, where you're maximizing your indoor air quality regarding bacteria, ozone, pathogens, et cetera, like that. Here's your site chart with all your components on there. What we're going to talk about today, or just focus on, is a dry bulb temperature. This is along the x-axis on the bottom. This is what you would see on a thermometer. On the y-axis, we have our specific humidity, which is also known as your humidity ratio. This is the amount of moisture that's as a water vapor that is in the air. The units that are used for specific humidity are pounds of water vapor per pound of dry air, or grains of moisture per pound of dry air. The conversion between the water vapor pounds and moisture is basically 7,000 grains equals 1 pound of moisture. There's a conversion for 60 grains. And then just want to highlight what I've seen mostly used, probably just from a conceptual standpoint or standpoint, is that the more common use of the units is grains of moisture versus the pounds of water vapor. Next is relative humidity. This is a ratio of the water vapor in the air compared to the maximum amount that can hold at the same air and pressure, temperature and pressure. This is a common weather report term. You have your different lines going from 0 to 90%. Way over on the left is 100% RH, which is the maximum amount of water vapor. So you have a condition with 60 grains of air at a certain dew point temperature. That same dew point temperature, that air can hold up to 132 grains. So that means that your relative humidity is a ratio of 60 to 135 and 45% as shown on your site chart there. In part two, we'll also call this vapor pressure that we'll talk about in part two when we talk about the lower dew point temperatures. Dew point temperature, temperature at which water vapor leaves the air as a liquid. That liquid, the water vapor condenses out of the air as condensate. You read the dew point temperature at the saturation line. Lastly, just a couple processes associated with DOAS unit. We have 8 different processes available. The one for today that I'm going to highlight is just the cooling ones, essentially. So you have sensible cooling, where you travel horizontally to the left on your site chart. Number 4 is dehumidification, where you're providing latent cooling, that is straight down, where you're removing moisture from the air. Number 6 is cooling and dehumidification, or total cooling. It's a combination of sensible as well as latent cooling. And then the other item associated with DOAS units is sensible heating. That's number 1 there, where we're going to reheat the air after it leaves our evaporator. So on our site chart, you have your entering air condition, your leaving air condition. First off is sensible cooling, where you're not removing any moisture. You stay constant in this situation at 89 grains, but you're reducing your air temperature from 95 to 75. Latent cooling or dehumidification is where you're keeping your dry bulb temperature constant, but you're removing moisture from the air. In this situation, we're going from 89 to 30. And then total cooling is just a combination of adding sensible cooling as well as latent cooling. All right, so on our site chart, we have our space temperature at 75, 50%. That is 55-degree dew point temperature. We have our outside air that's warmer as well as contains more moisture than our space temperature. What we want to do with our DOAS unit is we want to cool and dehumidify that air approximately into that red box area. What we're doing is our leaving air dew point temperature is less than or equal to 55 degrees. And then our dry bulb temperature that we're leaving from the DOAS unit is less than or equal to 75 degrees. The 75 and 55 are equivalent to our space temperatures. All right, so now on our outside air, using a package DX system, we have, once again, our outside air and space conditions. From point 1 to point 2, first we're doing sensible cooling, where the air is being cooled, driven horizontally. Stage 2 is going in the lower left-hand direction from, say, 2 o'clock to 7 o'clock. That is total cooling. We're removing sensible and latent heat from the air. Stage point 3 is we're reheating the air with sensible heating. And then what we're using in our HVAC system or package system is to cool the air, we're using the DX cooling system. And then to reheat the air, we're using 2 components. We're using hot gas reheat from the DX system, as well as a little bit of heat from your fan motor. Explaining DOAS in a couple slides. Here's a simple schematic of a DOAS unit up on a roof. You're taking outside air and then feeding it into the space. If you go through the definition or the name of dedicated outside air systems, dedicated means that it's separate from the other HVAC equipment. Outside air is that we're providing 100% ventilation air, that is to satisfy code as well as to provide good indoor air quality. And then the last part is the system, is you have your DOAS equipment. That's going to include heating, cooling, dehumidification, as well as filtration. And then in addition, it's a system, so you have to include controls as well as a duct distribution system. And then also associated with our DOAS system is we have ancillary or auxiliary units, where this is a little bit poor picture, but inside your space, you have auxiliary air conditioning and heating units that recirculate air within the space. So with our space, the summary of the cooling and dehumidification loads is comprised of 2 parts. The first part is associated with outside air. The outside air requires latent cooling, where we're removing moisture, as well as sensible cooling. And then in addition, our space has latent cooling as well as sensible cooling requirements. These are due to the space having lights, solar from windows, walls, computers, people, processes, et cetera, like that. And then just what is happening in our industry is that the amount of sensible heating from the space is lessening. This is due to improvements in lighting, energy, more efficient computers, as well as better windows and better building envelopes. What I want you to realize today is that your latent cooling associated with the moisture of the outside air is your most critical item that you want to address. Next slide here talks about the outside air. Essentially, 80% of a building's annual dehumidification load is associated with outside air. This is a chart here that shows that just latent cooling load associated with the outside air is typically 3 to 5 times greater than your sensible cooling load. This chart, has a couple of different cities. I've just highlighted Pittsburgh and New York. That was the closest one to our territory. In Philadelphia, Harrisburg, Scranton, et cetera, as well as Delaware and South Jersey. The blue bar just indicates the amount of latent cooling, and then the pinkish, reddish bar indicates the amount of sensible, right? And then just these two tidbits came from that ASHRAE handbook referenced down in the lower left-hand corner there. So with our cooling and dehumidification loads associated with our space, which are going to be satisfied by the DOAS unit, and then which are going to be satisfied by your auxiliary air conditioning or HVAC unit in the space. So your DOAS unit always takes care of your outside air sensible and cooling load, and then you have two options regarding your space sensible. The first one, the DOAS unit is going to provide neutral supply air, which is at room conditions. In this situation, your auxiliary units that are in the space are going to handle the space sensible and cooling load. Next, for option 2, once again, your DOAS unit is still taking care of your outside air requirements. Option 2 is your DOAS unit is going to provide drier or lower dew point supply air. The DOAS unit is going to take care of the space latent cooling load. This is also known as space latent load offset. This is what I'll call it today. There's probably a couple other different names for that. And then in this situation, your auxiliary unit is now only going to take care of the sensible cooling load associated with the space. With option number 2, when you do this arrangement or this design, what ends up happening is your DOAS unit is typically a little bit larger in capacity, and then your auxiliary units are smaller in capacity. These are when compared to option number 1. Now, option number 1, we're looking on a site chart where we're providing neutral air. Once again, we have our outside air conditions that are warmer and moister than our space temperature. What we're going to do is cool the air and dehumidify it, and then we're going to reheat it. In this situation, option number 1, your leaving air temperature is at the same dew point temperature as your space temperature. Once again, your auxiliary unit in this situation is going to handle the space cooling and latent cooling loads. Option number 2, the space latent load offset. We're providing drier supply air with a lower dew point temperature. In this situation, the DOAS unit is going to take care of the space latent cooling load. Back to our site chart. In this situation, option 1 had a dew point temperature equivalent to the space dew point temperature. But what we're doing in option number 2 is we're driving our leaving air temperature to be lower than our dew point temperature. So in this situation where leaving air temperature is less than a 55 dew point, that lower air, drier air that's provided by the DOAS unit is going to provide the space latent cooling load or satisfy that. So it could either do two things. It could either take care of the entire latent cooling load in the space or take care of some of the latent cooling load in the space. Once again, in this situation, the auxiliary unit is just taking care of sensible only cooling. And then once again, just in option number 2 versus number 1, the DOAS unit has a larger capacity and the auxiliary units have a smaller capacity because they're not handling the latent load in the space. The auxiliary HVAC units are always required with a DOAS system. They're required to control the space temperature. Some common examples of auxiliary units are water source heat pumps, VRF, fan coil units, as well as chilled beams or chilled induction beams, radiant cooling panels, as well as displacement induction chilled beams. all of these equipment, typically the latent cooling capacity is not their strong point. All right, and the benefits of DOAS systems, we're going to improve our indoor air quality. We're going to maintain our ventilation rates, satisfy our ventilation codes, our ASHRAE 62.1. We'll provide more accurate space humidity control. The better indoor air quality means better productivity. And then lastly, just what has occurred with DOAS systems in these, once again, unprecedented times associated, excuse me, with COVID, is that we're reducing our cross-contamination between spaces by isolating the DOAS unit as well as the auxiliary units. In addition, the DOAS systems or DOAS design can save energy. Will prevent ventilation of the space by providing too much outside air. Will provide the right amount of outside air that's needed for the space. With the DOAS equipment, because our outside air and exhaust air can be centralized, it's typically easy to implement energy recovery. And then energy savings, where you're not oversizing equipment, you can more accurately match your system loads. In addition, potential cost savings occur because of you are simplifying your HVAC system, you're simplifying your outside air and auxiliary control systems, and then in addition, with option number 2, with the space latent cooling load, if we increase the size of our DOAS unit, we're able to reduce the size of our auxiliary equipment, and we might be able to also reduce the size and cost associated with utilities providing those auxiliary units, the pipes, boilers, chillers, et cetera, like that. Okay, so the DOAS applications available. Basically, any type of building is eligible or a good candidate for DOAS systems. Buildings that have strict requirements for indoor air quality, for ventilation, for humidity control, as well as high energy efficiency are even better candidates. And then lastly, if you have a design in a humid climate where it's very important for indoor humidity control, this is an excellent candidate to install a DOAS system. And then in addition, spaces or just buildings and spaces that require higher than what I'll call normal outside air, such as hospitals, laboratories, manufacturing processes, et cetera, like that. These are once again excellent candidates to design using a DOAS system. Okay, next we're going to talk about the leaving air design of DOAS equipment. First off, airflow, just to kind of generalize, the airflow is typically sized for your outside air CFM. You typically follow ASHRAE 62.1. What I'm more concerned about today is your cooling capacity. What I'd like you to do is size the DOAS equipment for your latent cooling requirements. We're going to try to provide accurate humidity control. We're going to try to remove moisture from the air. We're going to design to a specific leaving air dew point temperature or leaving air grains. Once again, on our site chart, our leaving air dew point and temperature is associated in this type of area. So first off, what are your design conditions that you're using for your DOAS system? ASHRAE has, for different states and cities around the countries, airports, et cetera, they have different design criteria for 0.4 hours per year, 1%, as well as 2%. In parentheses is just how many hours per year that's associated with. And once again, a lot of engineering firms also have different criteria. So an example is, Philadelphia's temperature is 92.5, but a lot of engineers will just use 95 for dry bulb around here. So now for your design conditions, are you using your dehumidification design conditions? This is associated with the maximum latent load of your outside air. For Philly, this equivalent to 128 grains, approximate location on your site chart there. Or are you using cooling design, which is sized for your maximum sensible load? Once again, on Philly at 0.4 hours per year, they have a little bit higher dew point temperature, but lower grains. I would recommend for DOAS equipment to use your dehumidification design to ensure that you're providing the necessary dew point and leaving air dew point temperature and removing as many grains as possible. So here's an example of using an AON unit looking at the two different outside air conditions. I've got a unit with 3,000 CFM of outside air. I've used the Philly 0.4 conditions, and then I'm sizing the leaving air to provide neutral air. So using your dehumidification design with the 16-ton unit, we have an output of 122 MBH of latent cooling, about 10 tons out of that 16, so that's at our dehumidification design. If we use our cooling design, that same 16-ton unit is only providing 80 MBH of latent cooling. So just once again, be careful as to what are your requirements for your latent cooling, and then what are your outside air design conditions that you are using. Next, those were the outside air conditions. What are your space conditions? Usually this is easy to achieve or attain from your owner, from your occupant. Is it at 75, 50%? Is it at 70, 50%? Is it at 65, 40%, 45% RH? Next, what tolerances are allowed for relative humidity? Is it plus or minus 1%? Is it plus or minus 3%, 5%? And then also for your dry bulb, what is the tolerances allowed? Is it plus or minus a degree? Is it 3 degrees? Is it plus or minus 5 degrees? What you're going to do is the upper limit of your space. What is the upper limit of your space conditions? This is usually what you use for design conditions. Just an example, drawing up a site chart. We have our space at 70 degrees dry bulb and 50% RH. You have a tolerance of plus or minus 5 degrees as well as plus or minus 5% RH. So I drew just a little box to show where your acceptable space temperatures would be. So now for our upper limit, are we going to take the full, range of 75, 55? Are we going to use 73 to 50, 73 dry bulb, 53% to give us a little bit of safety factor? And then once again, the difficult part becomes, okay, how accurate is your space loads? Is your outside air accurate? How many people? Your lighting, computers? And then what our office has found is that a lot of times if we're providing a DOAS unit for a process, it's very difficult to get the information regarding what's the sensible heat gain, what's the latent heat gain from that process that is in the space. So here's an example of comparing our space design temperatures. We're using the same 3,000 CFM of outside air, the same option number 1 where we're providing neutral air. In this situation for my outside air design, I use the Philly 0.4 dehumidification design conditions. Here's what our DOAS unit's going to do. It's going to cool the air and then reheat it. So design number 1, if we have a leaving air temperature with a 58 degree dry bulb, we're approximately 75, 50% RH. That unit would, to cool down to 58 degree dew point temperature is going to be approximately a 14, 15 ton unit. If we were going to design number 2, option number 2, with a leaving air temperature of a 51 degree dew point, there's a big difference, obviously, you can see between the 58 and 51 degrees. Design number 2 is trying to have a 70 degree, 50% RH space. Design number 2, turns out to be a 20-ton unit. So once again, just be careful of what criteria you're using for your space conditions, because the changing the dew point temperature can have a large effect on your cooling capacity. So now if we have option number 2 where we are going to design for space latent load offset, we have to perform additional calculations. What you're trying to find is how dry to make your DOAS leaving air. So you have your space at 70 degrees dry bulb, 50% RH with the 51 degree. What you're trying to do is have a lower leaving air temperature. We're going to offset, the DOAS unit is going to provide some of the latent cooling from the space. So in this example here, do we have a leaving air temperature of 49 degrees dew point or 47 degrees dew point? The formula here is just the cooling latent load that's required. It's a constant 6.69 that depends on your air conditions. It's times your CFM times your change in grains. CFM is your space outside airflow. Q latent is the space cooling load. If you rejigger the equation there, and you want to find out what your leaving humidity ratio is, or grains, you would just have your leaving desired leaving air grains from your DOAS unit is equal to your space minus your load there. Once again, the space you want to probably use is your upper limit of your design criteria. Okay, next we're going to quickly just review DX refrigeration in your packaged DOAS equipment. Here's a typical refrigeration schematic where you have your main components. You have your A is your compressor, B is your outdoor condenser coil, C is a hot gas reheat coil, D is your expansion or metering device to adjust your refrigerant flow as well as reduce the pressure. And then item E is your evaporator coil. So you have your blue is your DOAS unit that enters your unit. It then first goes through your evaporator and then goes through your reheat coil. So on our package unit, the first part is cooling and dehumidification. Point 1, this is going through your evaporator coil. This is shown once again on the unit there where it is on your airstream as well as on your site chart. And then that air is going to be dried out, and then it's going to be too cold to be sent into the space. So we're going to point your sensible heating. We're reheating the air. We're going to use your reheat coil, and that's shown just once again on our site chart. Going from point 2 to point 3, and then your air going from point 2 to point 3 inside of the rooftop unit. Once again, a common slide, or just nothing new. The benefits of a packaged DX system from an equipment standpoint. You have components that are pre-engineered. You have your refrigeration components pre-engineered, already figured out. You don't have to do that in the field. It's a repeatable manufacturing process that typically results in high quality. You have factory testing, you have factory certifications, there's also quality assurance programs, et cetera, like that. But the main thing that I feel is that the strength of packaged DX unit is the controls. The controls are factory installed, they're factory wired, they're factory tested for continuity. The systems have been pre-engineered where locations of sensors, sequence of operations, et cetera, like that. And then lastly, the economics. Lower equipment cost of a packaged unit versus a built-up system, lower installed cost, and then typically I find that it's easier to service and troubleshoot because the packaged unit has everything kind of in a single spot from a component standpoint as well as a control standpoint. These next two slides are probably the most important ones of today. So with packaged DX unit with DOAS, we do have limitations. I will just say that the limitations are different for different manufacturers, but typically for your minimum leaving air dew point temperature, with your straight DX system, it's approximately 45 to 47 degrees dew point temperature. You can achieve a little bit lower if you do add hot gas bypass. The one thing I want to just point out is that operating at these low-ish leaving dew point temperatures, you just have to be careful because you're operating towards what I would call the edge of the operating envelope of your refrigeration system. And then just your minimum dew point temperature can be application specific. Where's your job site located? Is it up, up north, or is it down south where it's more humid? What are your temperature and relative humidity set points as well as tolerances? Is it an office or a school, or is it a clean room or a manufacturing process that are probably have a more critical application? Also, what type of auxiliary equipment do you have? Do you have water source heat pump that do have a little bit of latent cooling capacity? or do you have available, or are you designing with a sensible chilled beam where you don't have any latent cooling capacity available? So it's much more important to accurately size your DOAS equipment. And then finally, is it neutral air application or your space latent cooling offset application or design? And then the other thing to consider is that if you do have an energy recovery device, because you're utilizing the energy recovery device in the summertime, your entering air temperatures are a little bit, not as radical or much of a difference to cool air from 95, 78 to down to 55 or 45 versus if you're starting in the 80, 67 degree range. From a minimum airflow perspective, your evaporator coil should have a velocity of greater than 100, 150 feet per minute. Your supply fan, has, turn down requirements. A lot of these, I put 25%. What I found mostly is you can turn down around to 50%. But then once again, this is highly dependent on your external static, your CFM, as well as the fan curve or the fan type that you selected. And then just didn't talk about any of this today, but you also have to be concerned or consider your minimum airflows associated with electric heaters or gas heaters, as well as energy recovery devices, right? So from a cooling capacity turn down perspective, I'm going to recommend to have digital scrolled or VFD inverter compressors. So your digital scroll compressors has a turn down of approximately 5 to 10%. Your VFD, depending on the number and the size, can be anywhere from 5 up to 40%. If you have 4 compressors, you probably can turn down to 10%. If you have just 1 compressor, your turn down might be in the 20%. It's all different VFD manufacturers as well. Next, just want to emphasize that you should be designing for part load capacity control. This is a chart that I found on the internet. What they did is they recorded the temperature and moisture at JFK Airport for 1 year. They then plotted the number of hours on their site chart. If you look at the site chart there, the most hours of operation or that occurred are in the reddish, and then the least hours are in your dark blue. So just realize that your system designing, you're designing it for 0.4% design conditions. I just approximately plotted where your dehumidification design is, your cooling design, as well as your heating. Just once again want to emphasize that 0.4 hours per year is about 35 hours per year. So you're not going to operate very many times, very frequently in those situations. You're going to operate most of the time at part load conditions. You can see here just the yellowish and reddish, orangish hours are closer to part load conditions. And I also too want to just emphasize that they are closer to the, in a relative humidity standpoint versus your space temperature. So from a capacity standpoint, you want to emphasize accurate capacity control. The 2 components that you should be concerned about or focus on. First is your compressor. There's where it is in your refrigeration system. Your compressor is providing the capacity for the cooling to go from point 1 to point 2 on your site chart there. Just the types that you do have available are on-off, 2-step or 2-stage. Oops, sorry, Piper. Digital. That was my fault. Sorry about that. What I want to emphasize, you also have digital scroll as well. These are all scroll compressors. Digital, want to highlight in yellow that you should be providing a digital scroll or variable speed inverter. That's what you should be designing and using. Just these, as you increase your turn down capacity, your accuracy, you'll have longer on cycles and shorter off cycles. Next, on your hot gas reheat system, there's a picture of it shown there on an AON unit. There it is in your reheat coil. When I say system, it's the coil as well as the controls associated with it. On your site chart, we're using the reheat coil to go from point number 2 to point number 3. The types you have available are on-off as well as modulating. Just once again, want to emphasize that you should be, please be providing or speccing or designing with modulating hot gas reheat control instead of on-off. Okay, last couple slides here. Okay, last couple slides here is just going to quickly give an overview of the available DOAS equipment as well as auxiliary equipment that we have available at H.C Nye here. So H.C Nye has been around since 1977. We're manufacturer's representative of engineered, applied, and industrial HVAC systems. We're not just providing equipment, we're also providing service/warranty as well as parts. Buck Nye is our president. There's our website there. And then just, a lot of people with a lot of experience. So we're providing support all the way from beginning design all the way to final commissioning. All these different types of equipment we have available in systems and all these different types of applications that we are familiar with. Our staff has over 200 years of experience. We have 2 offices where they each have equipment sales, service/warranty, as well as parts stores. That upper right is a picture of our training room that's collecting dust ever since COVID happened. All right, and then, so here is the available DOAS equipment that we do have available from H.C Nye. You can read the list there, not going to really go through it, but I just want to highlight the ones that are in yellow are contained DX refrigeration systems. So that's Aon, Annex Air, Desert Air, Renew Air, as well as Semco. I'll just talk a little bit about each of those different products. First off is Aon. There's their website. Aon produces custom and semi-custom air handlers, rooftops, energy recovery units. It was founded in 1988. In 2020, they had over $514 million in annual sales. They have 2 facilities, 2 manufacturing office facilities, one in Tulsa, Oklahoma, the other in Texas, which is east of Dallas. Very large manufacturing facility. All of the, Aon is a total 100% U.S. company, manufactured, engineered, headquartered, owned United States. There's a picture of a line there. Just Aon has been known for total owner value for ever since their inception. They produce high quality units that are energy efficient. They have ease of serviceability in mind. They have application flexibility. They have always been very innovative with updating components and controls with the latest requirements of the HVAC industry. And then they also have an extensive and robust control system. The DOAS units are available from 2 up to 240 tons. They could be air-cooled or water-cooled. Want to just highlight a nice feature available is an air source heat pump. I've been trying to push air source heat pumps because of their energy savings in the mild wintertime versus gas heat, as well as their ability to provide more accurate heating control, once again, in those milder temperatures versus a gas-fired burner. All these DOAS units are available, with different controls and different applications. They're available with and without energy recovery. And then, once again, sophisticated controls that are so sophisticated, I had to, put it down on 2 different slides. I just want to emphasize once again, too, that we do have Aon parts available in both our stores in Harrisburg as well as King of Prussia. Next, Annex Air, company out of Montreal, Canada. They've been around since 1998. They specialize in factory testing as well as controls, very innovative. They specialize in energy recovery with the different types of energy recovery devices available. They do have a custom DX capabilities where they can provide water-cooled or air-cooled units up to 300 plus tons. What we've had a lot of luck with them is designing units that have 100% redundancy, where they have 2 separate DX systems in the same airstream. We've also designed them with dual path units, where you have a complete rooftop unit side by side with one airstream, and then if that fails, they can switch over to the second one as a packaged application for redundancy. Desert Air has DOAS units. It's not just used for natatoriums or grow rooms. They're out of Milwaukee, Wisconsin, just because they are typically associated with pool applications or natatorium applications. They do have a long history of experts in moisture removal. These are the two lines that they have available for packaged DOAS unit. Can be indoor, outdoor, water cooled, air cooled, with and without energy recovery wheels, and then up to that CFM. There's up in the right is Desert Air's website as well. Next is Renew Air. Renew Air focuses or specializes in a static fixed plate with a total energy recovery. Just want to emphasize, show that they're, we're the H.C Nye is a rep, except in Delaware, that's Building Systems and Services. Renew Air has been around since 1977. As I mentioned, they focus on, or their specialty is a membrane for the total heat transfer plate up to 11,000 units. And then recently they've come out with not just units with hydronic coils or energy recovery wheels and fans. They've also started to produce units with DX coils as well as packaged DX DOAS units. Next product is Semco. Semco is out of Columbia, Missouri, been around since a long time. They are typically known for their sensible and total wheels, up to large CFMs. They have an aluminum matrix versus, a little bit higher quality versus a polymer or a paper one. Semco is well known for their molecular sieve, true 3 angstrom design. That 3 angstrom has extremely low exhaust air transfer ratio. That's the amount of air that's transferred from your exhaust air to your outside air. The performance is HR 1060 certified, which oftentimes you don't find available with energy wheel manufacturers. Their specialty with this True 3A is the matrix coating, where they can provide a unit acid resistant, microbial, anti-stick. These are used down at Johns Hopkins to recover energy from class 4 laboratory exhaust air, to recover energy to save to the outside air to save energy, as an energy recovery always does. What Semco has regarding DX is a packaged DX. The first product is a Pinnacle. This uses a passive desiccant. This typically has a leaving air dew point of around 40 degrees or 40 grains. It's available in those sizes. They also have an Ascendant that uses an active desiccant. They have a leaving air dew point of 20 degrees, or they can even have lower grains. Both products are associated with low energy use and tight dew point control. And then with these lower dew point and grain leaving air conditions, we'll talk about these products or this type of system more in part 2, where we're going to talk about the lower dew point temperatures. Now, also associated with the DOAS units, we are required, or just we need to put in auxiliary units. So once again, H.C Nye is providing system sales, not just the DOAS unit, but we can also provide the auxiliary units. Different types available from a water source heat pump. We have Whalen, we have Aon. Carrier is also available in Central and Northeast PA. From a VRF perspective, we have Gree out of North America. From a fan coil perspective, we have 3 manufacturers. Whalen, once again. Naylor out of Houston, Texas. Naylor has some customization capabilities associated with fan coils in terms of heavier, thicker tubes, custom enclosures, great for retrofits, et cetera, like that. And then in addition, Carrier up in the Central and Northeast PA has fan coils available too. Next auxiliary products that we have available, these might be a little bit more associated with strictly sensible cooling. We have Semco chilled beams. We have New Climate that also makes sensible chilled beams, as well as induction beams that can provide some latent cooling capacity. We have radiant panels from Zender Rittling, which is hard to pronounce after you've been talking for 50 minutes or so. And then lastly, we have displacement induction chilled beams by Carson Solutions. These are typically associated with classrooms where you're using a DOAS unit to provide outside air to a a box that has a chill beam inside of it, and it's using induction to heat and cool the air in the space. Okay, last couple slides. Just what I wanted to highlight and try to emphasize today. DOAS systems are available for a wide range of applications. They can provide superior humidity control. They can provide excellent indoor air quality, as well as satisfy your ventilation and outside air codes. Your DOAS selection is critical. You want to emphasize or focus on humidity control. You're removing moisture from the air. You're using your dehumidification design conditions, but you want to make sure you're selecting for the right leaving air conditions. You want to select the unit based on your design conditions, but you're going to once again be operating at part load conditions. Want to emphasize once again to be cognizant of providing capacity turn down, so you don't you can provide constant operation in steady conditions instead of having equipment turning on and turning off. Next, the benefits of packaged DX equipment. You have lower first cost, easier control. Typically, we find that there's less problem versus a built-up system. And then once again, H.C Nye, we're providing system sales. We're not just providing sales, but we're providing parts as well as warranty and service. We can provide the DOAS equipment, and as we can also provide the auxiliary equipment, as well as obviously help you with your design and application as necessary. All right, and that's my last slide, and then just we'll take questions now. Want to just say that we're going to have part 2 in the September, probably September 14th, but I haven't picked the date for that yet. In that application, or in that seminar rather, webinar, we're going to discuss or just review using lower leaving air dew point temperatures, less than 40 degrees, where our typical traditional refrigeration system can't cool the air to a low enough dew to incorporate or an active desiccant wheel. All right. Once again, want to thank you all for attending. Want to just remind you that we do have a PDH credit available, and then Gina has updated our simple survey. We'd appreciate if you could take the time to answer that. The survey helps us provide better webinars, and then also to which topics are important for our customers in the industry. All right, thank you once again. Okay, where'd Buck go?
I'm right here.
Yay!
Can you review your recommendations for heat pump versus gas?
Yes. So essentially, I don't think that there's really any, off the top of my head, I don't think there's really any situation where the airside heat pump is not better than providing gas. I mean, I just want to also emphasize is that we're not totally eliminating the gas heat. The gas heat is still going to be required at your extremely low outdoor air temperatures. The airside heat pump would often have difficulty of going into defrost cycle. The airside heat pump, the strength is at the more moderate heating conditions, where say it's going from 25 degrees ambient up to 50 degrees. The airside heat pump will save you energy versus the gas heat, and then also too, it would provide more accurate leaving air temperature control. Want to just make sure you realize that your gas heater is sized for your design conditions. Whether you have a wheel or not, that could be from a 40-degree rise or a 60 or 80-degree rise. Just the gas heat has trouble operating when you're at those milder outdoor temperatures, and your gas heating requirement for temperature rise is 10 degrees or 15 degrees versus it's designed at 40 or 60 or plus, et cetera, like that.
Okay. Next question. Are all the DOAS units AHRI certified? So I'm going to jump in on this one. So ARI certification cuts off at, what is it now, 40 tons, Jim, for package?
It might be 60,
Might
but
be.
yeah.
So as far as packaged units go, AON is certified all the way as high as you can go. When you start getting into the larger product, 70, 75, 150, 200, they do all their rating and testing in accordance with what AHRI recommends. AON has a pretty substantial test lab that they run their units through the paces there. So I hope that answers your question. But from 2 tons up to 60, yes, they are. The packaged units are AHRI certified. In regards to the air handling units, like a Semco, I know their components are certified. I don't know if the systems are. Like the wheels have the certification, coils are certified. Anything else you can think of, Jim?
Correct. Yeah, I would agree with that. Same with like Annex Air is making a custom unit. So if you have if you have a redundant unit with 2 refrigeration systems in the airstream, that kind of throws out like the requirements, or just doesn't qualify, or just it doesn't fall under a nice category within the ARI certification.
Next question is, can you comment on the reliability of digital scroll versus variable speed scroll compressor technology? Which is a better way to go? So that's an interesting question.
Yeah.
You have different thought processes. The digital scroll has been around for, I believe, over 10 years now.
At least.
It has provided great reliability. The biggest concern that we've always run against with digital scrolls has been, from time to time, people hear the digital scroll unloading and they think there's a problem with the compressor, when there's not. The variable speed compressor will give you turn down, but it does not give you the turn down as far as the digital scroll will. We have both. The digital scroll is a more cost-effective option than the variable speed scroll. And as technology gets better, I'm sure we'll start seeing the variable speed scroll come down in price. But there's a lot of things with the variable speed scroll that you cannot get down to 10% load on a 10-ton unit. You might only be able to get down to 45 or 50% load. So, anything else you want to add to that, Jim?
Yeah, just with the with the VFD, what not just the cost of the VFD, but then you also have to change your expansion device to from a thermal one to a thermal one to an electronic, just to keep up with the more accuracy, and then also too with the variable speed scrolls. There's also a concern with oil circulation, so they end up adding some sensors and stuff like that. But I mean, Eric, to answer your question, I can't really say that we've had more problems with a variable speed versus a digital scroll. Like Buck said, the manufacturing is improving, reducing the cost, but then also too, variable speed are used in tons and tons of VRF systems, and my understanding is those have been pretty reliable.
Okay. The next question is, what are the economics of allowing higher outdoor air humidity and temperature from the DOAS versus having a hydronic fan coil take a larger part of the load?
George, when you say economics, I'm going to assume you mean first cost as well as operating cost. What I would say is that when you so what you're asking is that option 1 versus option 2, where option 1 was providing neutral air And then option 2 was providing the lower latent. Option 1, the auxiliary unit, was handling the sensible and latent, and then option 2, the sensible. So what the economics could turn out to be from a lower cost perspective, going with option number 2, is that yes, you're increasing the size of your DOAS unit from 10 tons to 12 tons or 25 to 30, but then the other side of that is the your auxiliary equipment in the unit goes from a 4-ton to a 3, or a 3 to a 2.5. So a lot of times, you're downside, you're increasing the size of one DOAS unit, but then you're downsizing, 15 or 10 or 25 units, auxiliary units, and then it's cheaper to downsize. It's cheaper for that option number 2 to downsize the auxiliary units, because then you can maybe also downsize your piping. Maybe if you have a chiller providing them, maybe you can go from 50 to 40 tons, a boiler, et cetera, like that. All right. Not sure if I answered that question, but I believe that's what you're looking for.
Sure. We got a couple. There's one that in the chat. So, are there options for chilled water DOAS units rather than DX? Absolutely. We can do chilled water with any of our vendors, I think, other than Desert Air.
Right. It's the thing you have to be, realize is that the DOAS units are typically reheating the air, so you have to come up with some, heat recovery for that. Your reheat's going to be attributed to your auxiliary systems.
Unless somebody wants to ask more, what needs to be coordinated with the control system as far as set points for VAV or constant volume? How do we assure that these conditions are met?
Okay, so for the controls, what you typically do is you divest the DOAS unit from the auxiliary unit. So your DOAS unit, you should control that to provide, depending on your outside air conditions, whether it's in cooling or heating or dehumidification or ventilation, the DOAS unit should be controlled to provide a leaving air temperature as well as a leaving air dew point. And then your auxiliary units should be controlling your space temperatures. You have a thermostat, and your auxiliary unit is typically cycling on and off or modulating to control those temperatures. So there's 2 other things to consider from a VAV or constant volume standpoint. The constant volume standpoint obviously is that situation where it's constant volume. You could do a DOAS system with the VAV if you install, say, CO2 sensors or occupancy sensors. Once again, the space isn't occupied. You either you probably shut off the outside air, or else you go down to a minimum. Lastly, the thing to consider is that it becomes more complicated if you're using that latent cooling offset. That the latent cooling, once again, is you have many different spaces. You are trying to provide a leaving air dew point temperature, and so it's a little bit more tricky, versus the neutral air conditions, because you're trying to satisfy the latent load in the space. But once again, your auxiliary unit is just tied into your space temperature sensor.
All right.
Thanks. Wow, I finished in an hour. I can't believe
it. We'll stick around for a minute or two if anybody has any other questions. Otherwise, thank you, everyone, for attending today. Really appreciate you giving us your time and hope you found that this was worthwhile for you. So, Jim, thanks again for doing a great
You're
job.
welcome, Buck. Thank you. Thanks for your help.
All right.